Hello everybody, well done for staying the course. I am the last speaker, so yeah, I'm pleased to see the room isn't completely empty. And thank you very much to the organisers of the event for the kind invitation to speak here today. Some really interesting talks, and I could spend probably the whole of my slot just commenting on some of the great points raised. I'm not going to do that though. So I'm going to talk about a few different things. I'm going to position some of the work that Nvidia and partners have been doing by talking about some of the clinical AI challenges and indeed the motivations, the benefits for that. I'm going to spend most of the time talking about Monai, which I'll explain what that is presently, because I think it's probably the most relevant of the sort of activities, and it's also the one that's closest to my heart because I'm very sort of closely involved with the development of Monai. And I'm going to talk a little bit about a couple of other technologies that may be of interest for some of you, and we'll see how much time we've got left for that. Okay, so AI challenges and benefits. So the graphs here, the details are not terribly important. On the left, this is actually waiting times in the UK, which, some people might be forgiven for thinking it's the Nvidia share price. It's not, and it's not the rate of my hair receding either. And it's also matched by the similar sort of chart, just talking about the anticipated demand for healthcare professionals in the US. So, and the point really being that, we all know the challenges that there are in terms of the gap between the resources that we're going to have available and the demand. And it's not just a UK problem, it's across the globe pretty much. So, it would be nice to think that AI can somehow just sort of step in and fill that gap. That's the sort of ideal scenario. But of course, as with everything, it's just not that simple. And in fact, AI has a lot of very unique challenges when it comes to healthcare. And a lot of these, issues have been very eloquently described today, particularly in the sort of the patient privacy and how to sort of try and have these trusted environments. But it really isn't that easy to deal with this. I mean, for example, if you're working in other domains doing kind of image processing, you might be able to use something like ImageNet, which is a nice, open source repository with nice clean images, all beautifully labeled. And of course, with medical imaging, we have noisy, multi-dimension images in which there isn't really any objective ground truth. In many cases, it's, very subjective. And that's quite apart from all of the challenges with standards. It's very interesting hearing about all the amazing work being done by groups that are obviously collaborating with one another, but there's a lot of sort of acronyms I've heard today I hadn't heard of before, doing similar sort of related things. And, that's a challenge for all of us. So, this is something, you all know about this, so I don't need to position that one anymore. In terms of the sort of benefits of clinical AI, and it's useful, I find, to think about the stakeholders involved here. We've got the clinical folks, we've got the technical, and we've got the commercial, and there are sort of intersections between all these. We've got sort of researchers who are, working in doing technical work, but using kind of clinical data, and we've got people like, healthcare providers who, again, providing instruments, that sort of stuff. They all need to sort of benefit somehow from this, but it's it's not easy to find a solution that ticks all the right boxes here. I mean, for starters, any new system that you introduce into a hospital, it has to not disrupt existing systems, obviously. So, one of the things which I've heard about several times is people trying to connect machine learning system to their PACS system, which is really not a good idea because, it's making all these repeated calls to these clinical systems, and then when somebody needs to pull a patient study, they find the network bandwidth has been completely hijacked. So this is obvious stuff, but I mean, there are more subtle issues that can arise if you try and use this sort of technology in ways that it wasn't intended. Of course, the other thing is what we don't want is for clinical staff to require extensive retraining to use new systems that are developed with AI. You know, to a large extent, the goal here is to use existing systems and embed newer technologies in ways that are sort of non-invasive. And that's not easy to do in a seamless way. We also want to try and adopt standards. A lot has been talked about that today. That's great. And of course, we need that sort of enterprise-grade robustness and scalability as well, which is often not a given with a lot of the sort of, you know, cutting-edge AI stuff. And maybe that's just, you know, because it's still relatively new technology. And of course, evidence as well is really important here. I mean, it's, you know, to build that trust in the previous slide, and of course, it has to, you know, we're talking about patient trust. There have been lots of studies that have shown that patients are mistrustful of AI. They would rather have a human to make that diagnosis, even when they're told that, you know, for this particular diagnosis, a computer will give you a more accurate answer. And usually the reason they give is that, well, they don't necessarily give it, but most patients think that their condition is unique, and so therefore they can't think that an algorithm would be able to factor in the uniqueness of their conditions. That's just more about psychology perhaps than computer science. And when it comes to clinicians, I always like to think that you know, trust is something that's earned osmotically and lost hemorrhagically. You know, unfortunately, it only takes one sort of, you know, misdiagnosis for an AI system for a doctor to question whether they can really trust that system. And, you know, from that point on, it's a sort of house of cards, really. Now, sometimes, of course, if you provide a reason why that system did what it did, then that can offset some of that, you know, sort of concern. And that's a really important part of this technology as well, being able to provide that evidence, not just sort of, you know, retrospective evidence about trials that have been done, but also evidence about, you know, which features it was on the image that were important in the diagnosis, those sorts of things. Okay, so with that in mind, this is really the sort of underpinnings behind what Monai is. So this is the Medical Open Network for AI, and it's an open source Apache 2 license initiative for medical AI. So for developers who are using machine learning, they're probably most likely using something like PyTorch. Monai is designed to be the medical imaging extension to PyTorch, if you like. So it works on a PyTorch foundation, but it adds extensions that do things that you know, standard PyTorch capabilities wouldn't provide. So, for example, there are lots of losses that are loss functions, lots of image manipulations. There are lots of networks that have been developed specifically for medical imaging. And they're slightly different. I mean, you know, they've got more dimensions, for example. They're using, you know, monochrome, perhaps. They are, you know, things like a dice loss function is something which is used, I mean, it is used in other domains, but it's very important for a lot of segmentation challenges in medical imaging. So Monai provides a lot of that sort of stuff, and that is in the Monai core part. So this is really for the part that researchers will be working with. Because one of the things that we find as well is there are kind of a couple of types of developer when it comes to deep learning. So the type that want to do everything themselves, usually researchers motivated by, you know, a novel method which they can publish. And then there are people who just want to get the best result possible they can. And Monai tries to cater for both of those groups. And I should say that the Venn diagram is not too separate. You know, you can do both of those at the same time. Yeah, we try and cater for all that. So, you know, Monai's got all the nuts and bolts if you want to sort of build your own novel network, but it's also got pre-built packages that you can run and execute in less than 5 lines of code. So you'll see we try and sort of span this gap between the research community and the sort of things which they generate, and then the actual application deployment part, which is the getting it into a hospital, getting it into real-world clinical use. And I'll talk a little bit about some of the methods that we use to do that. In terms of the sort of pedigree of the Monai community, so Nvidia and King's College London were probably the people who initiated this, but we announced this at a MICI conference, Medical Imaging AI, Computer-Aided, Computer-Assisted Interventions Conference, 2019, and we invited a lot of sort of leading folks from the sort of medical imaging community, from quite a diverse group, a lot from the US and Germany, and all around the place. So there are 11 working groups as well that meet on a regular basis. It's all open. It's all the notes from the meetings are on GitHub. All the code and everything is as well. I'd very much invite anybody who this is news to have a look around and see if there's something that you can help out with, because like many of the other speakers, we're always thinking about the sustainability of this, and we rely on the contributions and suggestions from kind of thought leaders on this. It's a sort of full stack thing as well. So obviously Nvidia is well known for its hardware, and most of Monai will run on any hardware, but obviously a lot of our GPUs are really optimized for these sort of AI-related tasks. We've got lots of, I'm not going to really talk about the hardware. Like I say, we build on PyTorch. You can also use things like TensorFlow as well. There's also things like Rapids, which is a machine learning, GPU-accelerated machine learning toolkit. And we have things like Triton Inference Server, which takes a trained model and executes it in a sort of scalable and reliable way. These are all parts of what is known as Monai. One other thing I should point out, some of you might hear the term Clara, which is used. That was an old name for what turned into Monai. And it's now used as a sort of umbrella term for any sort of healthcare products that Nvidia has. So if you're wondering what the difference between Clara and Monai is, that's it. Monai is available on all the sort of cloud providers. It's used by a lot of big name academic medical centers, used by a lot of enterprises. We've just exceeded 2 million downloads, which is not bad in sort of 4 years. It's also part of a lot of the sort of existing toolkits that are out there. Things like Nuance Communications use it. AWS SageMaker has this. It's available on GCP as well. And you can find it pretty much anywhere. There's lots of different ways of consuming it. So I want to just very briefly talk about some of the key workloads that are involved with this that you'll find here. So one of them is the generative AI stuff. There's a lot of, this is a relatively new part of Monai, but you can find a lot of diffusion-based models, these vector quantized variational autoencoders, lots of other state-of-the-art image generation networks. These can be really useful. And again, I know this was talked about a little bit about earlier, but I mean, what we found is that some organizations, they really struggle to get the diversity of data they need, and this can be a really good way of filling in the gaps in your data with synthetic data. And for people who are sort of concerned about, training on synthetic data, I mean, this is something that's been going on before these diffusion models, but we were doing things like, we've always done things like augmenting data before, which is a sort of crude way of achieving what this is doing. So it's nothing particularly new, and there are now some very large data sets that have been synthetically generated, which people can sort of pick and choose from to, and indeed networks that will generate, images to order that you can then include in your training data set. And if it boosts accuracy, that can only be a good thing. And that's often the case. That actually people will use some of these synthetic data sets as like a sort of base data, and then they'll add their own proprietary data to fine-tune the model for their particular use case. Oh, sorry, I didn't mean to skip on. AI-assisted annotation, I'll get to that in a minute. That's one of the really sort of cool things, I think. One of the industry trends as well is this auto ML. So I'll talk a little bit about that. So these 3D segmentation models. I'll probably skip over federated learning today because a lot of people have already talked about that. But Monai does have a federated learning component to it. And in fact, the Nvidia SDK called NVFlair was pioneered as part of our medical solution and before it was spun out into a more general solution. And then we have a couple of sort of tools which you can use, so say, for that sort of clinical deployment part. So for the synthetic image generation, I've mentioned actually quite a lot of this already, so I'll probably skip over it. But you can see these are some of the tools and models that you can find in this generative AI repo, which is part of Monai Core. You can build on foundation models, you can fine-tune them, or you can, completely retrain them. And you should be able to find models in our model zoo as well that will allow, provide this sort of stuff with a kind of just download a container and run a command, and it will just point it at your data, and it will just do it for you. And of course, the privacy stuff that's been covered quite a lot earlier, so I'm not going to talk about that. So AI assistance, this is such a cool thing. It demos really well. For people always interested when they see it, and it really fulfills this unmet need of how do we, we've got all this data. How on earth do we annotate it? How do we generate this ground truth? And what the AI assisted annotation tools that Nvidia provide, well, not Nvidia, but we certainly have probably provided the majority of the code, but it's all open source. And obviously we work with a lot of other collaborators as well. But it's basically this human-in-the-loop idea. So we take existing medical imaging viewers, which have got some nice annotation tools in there, like QPath for digital pathology, 3D Slicer for radiology, CVAT for sort of endoscopy, that sort of stuff. And we've basically created this API, it's a REST API, that provides AI. So what happens is you annotate, you have a data set, you load it up to the API server, it then looks at that data set, and you will usually start with one of our pre-trained models that understand the modality that you're working with. It may not understand the exact pathology you're trying to segment or something, but it has a really good understanding of CT, MRI, ultrasound. So it's normally pretty good at doing it. You have a go at segmenting whatever it is, and you correct it with the manual correction tools. It then in the background takes that, very aggressively augments the data and retrains. And after sort of 3 or 4 images, it's already got a lot better. But even more clever than that, it uses active learning technique. So it actually looks at the uncertainty in your training data given the current model, and it prioritizes the images that are going to add the most value. Because as you can imagine, there's a lot of redundancy in most image data sets. You'll have hundreds of examples of the same thing. So although it tends to prioritize the more tricky cases, which mean that they take more manual intervention, you can cut down the amount of annotation to achieve the same accuracy by a factor of about 75%. So you can use 25% of the training data to achieve the same accuracy that you're going to end up with anyway. And you can, so Charité in Germany, they published a nice paper on this, showing that how they managed to reduce their annotation time by 50%. And obviously it varies from use case to use case. This is really the future, I think, of a lot of AI, and this is this auto ML. This is really quite sort of cool but scary. So this is basically an end-to-end automated pipeline that uses all the techniques I've said, but it's completely automated. So it uses AI to train the AI. So it chooses the best model, it looks at the data set, chooses the best examples, it chooses the right ensemble of different approaches, it chooses all the hyperparameters, and this year it won 4 MICI challenges, which normally take leading experts in the field weeks to develop. It won 4 of them, and I'm told with less than 24 hours of model training. So unfortunately, I think that's probably going to be the future. So I said I'd skip over federated, and that's exactly what I'm going to do, because we're pretty much out of time. Two other things I am going to mention, though. One is maps and bundles. These are ways that you can package up AI models that have been generated in Monai. Bundles are really good for, if you publish a paper, you can create a bundle. If you used Monai to develop it, you can create a bundle which will allow anybody to basically download not just the code, but a working solution. And Monai has things like determinism in there, so you can actually make it so that they can train to achieve exactly the same binary result as you did, because it will eliminate the stochasticity from it. That's a really powerful thing for reproducibility. But similarly, you can use the similar technology called maps or Monai application packages to package things up and then run them on Monai Deploy, which is a sort of system that we designed for putting these, getting these things into hospitals. And again, we've got a red timer here, so I'm gonna leave it there. That's pretty much the end of the Monai stuff.
Thanks very much for that, Jonny. So we've got a couple of minutes for questions. We've got one over here.
Thank you, really interesting. I mean, all very cool stuff, as always in AI. Is explainability being engaged and involved in these works?
Yeah, I mean, so one of the things I didn't really have time to talk about was the sort of multimodal aspect of AI, and we're kind of emerging from this era where we've only been looking at just the images, not the clinical notes as well. That's starting to happen, obviously, but there's also an extension to that is the interrogatability of these images using natural language as well. So, and this is something that's starting to happen now. So in that use, there's a really nice use case for that situation where your model generates an unexpected prediction. I've seen a couple of people or a couple of examples where you can then ask the model or ask a different model to explain why. And what it will do is it will actually look up all the medical literature and try and match the prediction against why it might have come up with that. I think those sorts of things can be really powerful, and I think we're going to see more and more of that. But this is very sort of early stage. But like I said, I think this combination of different modalities will allow us to be able to sort of throw a lot more light on because image processing on its own is very it's an intuitive thing that we do, and it's the same for AI. But if you ask a pathologist or a radiologist to explain why, then it can make more sense. And if we can get AI to do the same thing, I think that could really help.
One more question, I think we might have time for. Carol?
I have a question from Helen Parkinson, remotely, who says, how are biases identified and evaluated in your tool set, as AI on AI sounds like a compounding problem?
Yeah, that's a good, it's a good question. Yeah, so the question was, how can you identify biases in the case where perhaps AI is training the AI in the first place? And that is, I think it's a really valid point. I mean, normally what we would do, of course, often the bias isn't so much in the training; it's usually in the data itself. Because the training mechanisms are automated anyway. So it's usually down to the selection of the data. Now, it's true that if you're getting an AI to try and choose a particular set of images that it's going to train with to maximize accuracy, then that could induce bias. But I suppose the way to do that is you can parameterize pretty much everything with these things, and if you want to impose as a minimum bias as possible, I'm imagining that we could probably have some sort of, control over that. I'm not quite sure what that looks like. That's not something I've sort of thought about, but technically it should be possible. And if it's not possible to do that, it should be possible to at least monitor the outputs for that in the same way that we do already you always try and make sure that it's performing well on the test set, minimizing bias. So I don't think anything really changes there. Yeah, exactly. Vortex, sort of, yeah.
So we will have to finish there. Thank you very much, Jonny, and thank you to the rest of the speakers this afternoon.